The planet. No one visits somewhere. Far beyond the warmth of the sun, beyond the golden haze of Saturn's rings, beyond even the pale orbit of Uranus. There is a world so distant that sunlight arrives there, faint and tired. A world so remote that, for most of human history, we did not even know it existed. Tonight, we begin our journey there, to a planet that moves slowly in the darkness, a planet that whispers instead of shines, a planet that may be hiding something. Wherever you are right now, whether you are settling into bed, resting after a long day, or simply letting your thoughts drift, imagine moving outward, out past Earth, past Mars and the asteroid belt, past Jupiter, massive and striped, past Saturn's luminous rings, past Uranus, tilted and strange, and then farther still, but into a region where the sun becomes just another bright star in the sky. This is where Neptune waits. Neptune is the 8th planet from the sun. It orbits at an average distance of about 4.5 billion kilometers. Light from the sun takes more than 4 hours to reach it. That means every sunrise on Neptune is already 4 hours old by the time it arrives. Every glimmer of warmth already weakened by distance, already fading. From Earth, Neptune cannot be seen with the naked eye. It hides beyond the limits of human vision. Even through small telescopes, it appears only as a faint blue dot. It does not dominate the sky like Jupiter. It does not glow golden like Saturn. It does not display dramatic rings or visible surface detail. It remains distant, quiet, almost deliberately unnoticed. And yet, Neptune is not small. It is nearly 4 times wider than Earth. It holds more than 17 times Earth's mass. If Earth were a small marble, Neptune would be a heavy blue sphere the size of a basketball. It is an ice giant, composed not primarily of rock like our planet, nor mostly of hydrogen and helium like Jupiter, but of volatile substances, water, ammonia, methane, compressed under immense pressure into forms we can barely imagine. It is a world of crushing gravity and supersonic winds, a planet wrapped in storms that rage in darkness, a sphere of deep cobalt blue, colder than almost any other place in the solar system. And yet, despite all of this, we have visited Neptune only once. In 1989, the spacecraft Voyager 2 swept past Neptune in a fleeting flyby. It did not enter orbit. It did not linger. It passed quickly, collecting data for only a few hours before continuing outward into interstellar space. That single encounter remains our only close look at this distant world. Think about that for a moment. We have rovers exploring Mars for decades. We have sent multiple missions to Jupiter and Saturn. We have landed probes on comets and asteroids. We have flown spacecraft beyond the edge of the solar system itself. But Neptune, vast and powerful, has been glimpsed only once, for just a handful of hours. Why? Distance is part of the answer. Sending a spacecraft to Neptune requires more than a decade of travel. It demands careful alignment of planets for gravitational assists. It requires enormous amounts of energy, funding, patience. Neptune is not easily reached. It resists quick visits. But perhaps there is something more subtle at play. Neptune does not demand attention the way other planets do. It does not blaze like Venus. It does not shimmer like Saturn. It does not sit close enough to inspire constant curiosity. It occupies the edge, the boundary, the quiet outskirts of our planetary family. And sometimes, what sits at the edge is overlooked. Yet Neptune has always been unusual. It was not discovered by accident. It was not found by scanning the skies randomly and stumbling upon a moving light. Instead, Neptune was predicted by mathematics before it was ever seen. Astronomers in the 19th century noticed that Uranus was not moving exactly as expected. Its orbit showed tiny irregularities, slight deviations from predicted paths. Something unseen was tugging on it. Two mathematicians, working independently, Urbain Le Verrier in France and John Couch Adams in England, calculated that an unseen planet must exist beyond Uranus, exerting gravitational influence. They predicted its position in the sky using only equations. And when telescopes were turned to that precise location in 1846, Neptune was there. A planet discovered not by sight, but by gravity. Even before we saw it, Neptune was already hiding, already influencing the solar system invisibly. There is something almost poetic about that. A world so distant that it first revealed itself only through subtle gravitational whispers. It announced its presence not through brightness, but through disturbance. Not through visibility, but through mathematics. Neptune's orbit is immense. It takes 165 Earth years to complete a single journey around the Sun. That means since its discovery in 1846, Neptune has completed only one full orbit. In 2011, it returned to the exact position in space where it had been when humans first observed it. 1 year on Neptune is longer than a human lifetime. Imagine living your entire life under a sky where seasons shift so slowly that generations pass before the planet completes a year. Imagine watching storms that last for years, winds that never truly rest, darkness that dominates most of the planetary cycle. The sunlight at Neptune is roughly 900 times fainter than on Earth. At noon, Neptune experiences something closer to a deep twilight than a bright day. The sun appears as a small, brilliant star, still brighter than other stars, but no longer the overwhelming source of warmth and light we know. And yet, despite receiving so little solar energy, Neptune is strangely active. Its atmosphere is alive with motion. Winds reach speeds exceeding 2,000 kilometers per hour, the fastest measured in the solar system. Storm systems form and dissipate unpredictably. Massive dark spots appear and vanish over time. Clouds of frozen methane drift high above deeper layers. It is cold, around -200 degrees Celsius at the cloud tops. And yet, it radiates more than twice the heat it receives from the sun. That detail alone raises questions. How can a planet so distant, so deprived of solar energy, generate such internal activity? Where does that extra heat come from? Why is Neptune more dynamic than Uranus, which lies closer to the Sun? The truth is, we do not fully know. And that is what makes Neptune different. Other planets feel familiar now. We have mapped Mars extensively, as we understand Jupiter's storms. We have studied Saturn's rings in exquisite detail. But Neptune remains partially veiled. Our knowledge is based on a brief encounter and distant telescope observations. There are entire layers of Neptune's atmosphere we have never directly sampled. Its internal structure is modeled, but not confirmed. Its magnetic field is tilted and oddly shaped, unlike Earth's stable alignment. Its moon Triton orbits backward, suggesting it was captured long ago. Its faint rings are broken into arcs that defy simple explanation. Each of these details is a thread, and together they hint that Neptune is not just distant. It is complex in ways we have not yet unraveled. Imagine descending slowly through its atmosphere. At first, you would encounter high clouds of frozen methane crystals, reflecting blue light. Beneath them, pressure increases steadily. The temperature rises. Hydrogen, helium, methane, water vapor mix under crushing force. Deeper still, beyond what any probe has reached, exotic forms of matter may exist, superheated water under extreme pressure, perhaps even rains of diamond forming in its depths. This is not science fiction. Laboratory experiments on Earth have simulated the conditions inside Neptune and suggest that methane molecules may break apart under immense pressure, releasing carbon that crystallizes into diamond. These diamonds could sink downward like glittering stones falling through a dark ocean. If that is true, then somewhere inside Neptune, in the crushing silence beneath its clouds, diamonds may be raining continuously. And we have never seen it. Neptune's magnetic field adds another layer of mystery. Unlike Earth's magnetic field, which is roughly aligned with its rotational axis, Neptune's is tilted by nearly 47 degrees. It is also offset from the planet's center. This creates a magnetic environment that wobbles and shifts as Neptune rotates. The cause remains uncertain. It may arise not from a solid metallic core, as on Earth, but from convective movements in an internal ocean of ionic water-ammonia mixture. But these are models, hypotheses, calculations. We do not yet know. Neptune's largest moon, Triton, deepens the enigma. Triton orbits in the opposite direction of Neptune's rotation. That retrograde orbit suggests it was once an independent object, perhaps a dwarf planet, captured by Neptune's gravity long ago. Triton is geologically active. It has nitrogen geysers that erupt from its surface, creating dark streaks across its icy plains. It may harbor a subsurface ocean beneath its frozen crust. If so, the Neptune system could host environments potentially suitable for complex chemistry, possibly even the precursors to life. But again, we have only glimpses. Triton's orbit is slowly decaying. Over millions of years, it may spiral inward and eventually break apart, forming a new ring system around Neptune, a future catastrophe unfolding in slow motion. And still, no mission is currently en route to explore these mysteries in detail. Neptune waits. At the far edge of the solar system, it turns slowly in the darkness. Its storms churn unseen. Its interior compresses matter into unfamiliar states. Its magnetic field twists unpredictably. Its captured moon erupts quietly into space. There is something about Neptune that feels unfinished, as if our understanding has barely begun, as if the most important details remain concealed beneath layers of distance and time. It is easy to overlook what lies far away, easy to focus on worlds that are brighter, closer, easier to reach. But sometimes, the quietest places hold the deepest secrets. Neptune is not dramatic in the night sky. It does not demand attention. It does not sparkle with obvious intrigue. It simply exists, turning, waiting, and perhaps hiding something that we have not yet imagined. Tonight, we begin to look more closely, because sometimes the most distant planet in our solar system is not just the farthest world. It is the one we understand the least. And in the darkness beyond Uranus, beneath faint sunlight and endless winds, Neptune continues to whisper. The discovery that shouldn't have happened. Neptune is the only planet in our solar system that was not discovered by accident. It was not first seen through a telescope and then identified as something new. It did not announce itself with brightness. It did not wander clearly against the background stars in a way that caught immediate attention. Instead, Neptune was discovered by mathematics. That alone makes it different. To understand why, we must go back to the early 19th century. At that time, astronomers had already identified Uranus as a planet. Uranus had been discovered in 1781 by William Herschel. For decades, astronomers carefully tracked its orbit, measuring its position against the stars and calculating its motion according to Newton's laws of gravity. But something was wrong. Uranus did not move exactly as predicted. Its orbit showed tiny irregularities, small deviations, slight drifts from the path that calculations suggested it should follow. These deviations were subtle, but consistent. And in astronomy, even the smallest inconsistency matters. If Newton's laws were correct, and by that point they had been confirmed repeatedly, then something else must be exerting gravitational influence on Uranus. Something unseen. Instead of dismissing the irregularities as observational error, astronomers began to consider a bold possibility. What if there was another planet beyond Uranus? A planet massive enough to tug gently on Uranus, altering its orbit just enough to create the discrepancies being observed. This was not speculation in the casual sense. It was mathematical inference. Two mathematicians, working independently, attempted to solve the puzzle. In France, Urbain Le Verrier began calculating the possible position and mass of an unseen planet that could account for Uranus's strange behavior. At the same time in England, John Couch Adams was conducting similar calculations. Both men used Newtonian mechanics. They assumed that gravity operated universally and predictably. If a planet existed beyond Uranus, its gravitational pull would distort Uranus's orbit in measurable ways. By reversing the equations, they could estimate where such a planet must be located. It was an extraordinary intellectual leap. They were not searching randomly across the sky. They were predicting a world that no one had seen. Le Verrier eventually sent his calculated position to the Berlin Observatory in 1846. On September 23rd of that year, astronomer Johann Galle pointed a telescope toward the predicted coordinates. Neptune was there, less than 1 degree away from where the calculations had predicted. This moment marked one of the most remarkable confirmations of mathematical physics in history. A planet had been discovered not through chance observation, but through pure reasoning. Gravity had revealed an invisible world. It is difficult to overstate how extraordinary this was. Up until that point, planetary discoveries relied on sight. Mercury, Venus, Mars, Jupiter, and Saturn had been known since antiquity because they were visible to the naked eye. Uranus was discovered with a telescope, but it was still visually observed first and understood later. Neptune reversed the process. It was understood first, observed second. This means Neptune's very existence was hidden, detectable only through its gravitational influence. Long before we saw it as a faint blue disk, we felt its pull through mathematics. There is something deeply symbolic in that. Neptune did not reveal itself directly. It altered the motions of another planet. It created disturbances. It shifted trajectories. In that sense, Neptune has always been a world defined by subtlety. The discovery also reinforced the power of Newton's laws. The equations describing gravitational attraction between masses were precise enough to detect a planet billions of kilometers away solely from its effect on Uranus. Gravity, once again, proved to be the quiet messenger of hidden worlds. But the story does not end there. After Neptune's discovery, astronomers continued to study Uranus's orbit carefully. They found that even after accounting for Neptune's influence, some minor discrepancies remained. This led to speculation about yet another planet even farther out. This hypothetical world was sometimes called Planet X. The search for Planet X eventually led to the discovery of Pluto in 1930 by Clyde Tombaugh. However, Pluto turned out to be far too small to account for the gravitational disturbances originally predicted. Later refinements in measurements showed that the discrepancies in Uranus's orbit had been overestimated due to inaccurate calculations of Neptune's mass. In other words, Neptune had solved the problem almost completely. It was the missing piece. Its mass is approximately 1.024 times 10 to the power of 26 kilograms. That is about 17 times the mass of Earth. Despite being smaller than Uranus in diameter by a small margin, Neptune is actually more massive and denser. Its average density is about 1.64 grams per cubic centimeter. That makes it denser than Uranus, which has a density of about 1.27 grams per cubic centimeter. These numbers matter. Density provides clues about composition. A higher density suggests a greater proportion of heavier elements. Neptune is classified as an ice giant, along with Uranus. This distinguishes it from Jupiter and Saturn, which are gas giants. The term ice in this context does not mean frozen solid ice as we imagine on Earth. It refers to volatile compounds such as water, ammonia, and methane. Under Neptune's immense pressure, these substances exist in exotic states, supercritical fluids rather than solid or liquid in the traditional sense. Neptune's radius is about 24,622 kilometers, and that makes it roughly 4 times wider than Earth. If Neptune were hollow and you could place Earth inside it, nearly 60 Earths could fit within its volume. Despite this size, Neptune appears small from Earth because of its distance. On average, it orbits about 30 astronomical units from the Sun. 1 astronomical unit, AU, is the average distance between Earth and the Sun. About 150 million kilometers. That means Neptune is roughly 4.5 billion kilometers away. To put that into perspective, if Earth were 1 meter from the Sun in a scale model, Neptune would be 30 meters away. Light, traveling at approximately 300,000 kilometers per second, takes about 4 hours to reach Neptune. This means any image we capture from Neptune shows the planet as it was 4 hours ago. Communication delay for spacecraft is similarly long, as if we sent a signal to a probe orbiting Neptune, it would take 4 hours to arrive. A response would take another 4 hours to return. 8 hours total for a round-trip communication. This delay alone makes real-time control impossible. Any mission to Neptune must operate autonomously for extended periods. Neptune's orbital period is 164.8 Earth years. It rotates relatively quickly, completing one rotation approximately every 16 hours. This rapid rotation contributes to the extreme dynamics of its atmosphere. Even before Voyager 2 arrived in 1989, telescopic observations from Earth had identified Neptune's deep blue color. That color arises primarily from methane in the upper atmosphere. Methane absorbs red light from the Sun and reflects blue wavelengths back into space. However, Uranus also contains methane and appears pale blue-green. Neptune is darker and richer in blue color. This suggests additional atmospheric processes at work, possibly involving deeper atmospheric layers or unknown chromophores that modify light absorption. The discovery of Neptune by calculation also introduced a new era in astronomy. It demonstrated that celestial mechanics could reveal unseen objects. This method continues today. Astronomers detect exoplanets orbiting distant stars by observing tiny wobbles in the star's motion caused by gravitational pull. In many ways, Neptune was the first example of indirect planetary detection. Its discovery proved that invisible forces could betray the presence of hidden worlds. Even now, astronomers are using similar techniques to search for a hypothetical Planet 9 far beyond Neptune. Some objects in the outer solar system display unusual orbital clustering that may suggest the gravitational influence of a yet undiscovered planet. If such a world exists, it would follow in Neptune's footsteps, revealed first through mathematics. The idea that Neptune was discovered before it was seen carries an important lesson. The universe does not always reveal itself through brightness or spectacle. Sometimes, It reveals itself through deviation, through subtle anomalies, through numbers that do not quite align. Neptune's existence was inferred from a disturbance. That theme continues when we examine its current behavior. Its internal heat output exceeds what simple solar heating would suggest. Its storms appear and vanish unpredictably. Its magnetic field is unusually tilted. Its moon Triton behaves in ways that imply violent capture events in the past. Each of these is a kind of deviation, a gravitational whisper, a reminder that Neptune may still be influencing its surroundings in ways we do not fully understand. In the next sections of our journey, we will move deeper into Neptune's physical characteristics. We will examine its atmosphere, its energy imbalance, its storms, and the questions they raise. But before we move on, it is worth pausing to appreciate what Neptune represents. A planet found by equations, a world predicted by gravity, a sphere that hid in darkness until mathematics illuminated its existence. Neptune did not step into view willingly. It had to be calculated into existence. And perhaps that is why it continues to feel mysterious. Because from the very beginning, Neptune has been a planet that does not reveal itself easily. It must be understood before it can be seen. A world at the edge of sunlight, Neptune orbits at the very frontier of the classical solar system. It is the last of the major planets. Beyond it lies the Kuiper Belt, a vast region of icy remnants and dwarf worlds. But Neptune itself stands as the final giant, the boundary marker between the familiar planetary realm and the deeper, darker outskirts of our star's influence. Its average distance from the Sun is about 30 astronomical units. That means it is 30 times farther from the Sun than Earth is. At such a distance, the energy arriving from the Sun is dramatically reduced. Solar radiation weakens with the square of distance. If Earth receives full sunlight at 1 unit of distance, Neptune receives only about 1/900th of that intensity. Sunlight there is faint. The Sun would appear as a small, brilliant star, still the brightest object in Neptune's sky, but no longer the overwhelming source of light that dominates Earth's daytime. The sky would not glow blue. There would be no familiar brightness. Instead, the atmosphere would sit in a permanent twilight, dim and cold. The temperature at Neptune's cloud tops averages around -214 degrees Celsius. That makes Neptune one of the coldest places in the solar system. It is important to understand that this temperature refers to the upper atmosphere. Deeper layers grow warmer under pressure. But at the visible cloud tops, the region we can observe, Neptune is extremely cold. Given this extreme cold and its distance from the Sun, one might assume Neptune would be quiet, frozen, motionless. Yet the opposite is true. Neptune's atmosphere is one of the most dynamic in the solar system. This creates the first major paradox. How can a planet so far from the Sun, receiving so little energy, generate such intense atmospheric motion? The answer lies partly in internal heat. Neptune radiates more than twice as much energy as it receives from the Sun. That means it has its own internal energy source. This excess heat likely originates from gravitational contraction and residual heat left over from its formation. When planets form, gravitational energy converts into thermal energy. Over billions of years, this heat slowly escapes into space. Neptune appears to be releasing internal heat more efficiently than Uranus, even though both are classified as ice giants. This difference between Neptune and Uranus remains one of the unsolved mysteries of planetary science. Uranus emits very little excess heat. Neptune emits significantly more. Yet they are similar in size, composition, and distance from the Sun. Something inside Neptune is still active. This internal heat drives convection within the atmosphere. Warm material rises, cooler material sinks. This circulation creates pressure differences, and pressure differences create wind. Neptune's winds are the fastest recorded in the solar system. Measured wind speeds have reached over 2,000 kilometers per hour. To put that into perspective, Earth's strongest hurricanes reach wind speeds of roughly 250 kilometers per hour. Neptune's winds are nearly 10 times faster, and they occur in an environment that is far colder and darker than any storm on Earth. These supersonic winds circle the planet in alternating bands, similar in structure to Jupiter's and Saturn's atmospheric patterns. However, Neptune's bands are less visually distinct. The deep blue color of the planet hides some of the internal turbulence. In 1989, when Voyager 2 flew past Neptune, it captured images of a massive storm system known as the Great Dark Spot. This storm was comparable in size to Earth. It resembled Jupiter's Great Red Spot in appearance, though darker. The Great Dark Spot was located in Neptune's southern hemisphere. It was an enormous vortex, driven by pressure gradients and high-speed winds. However, when the Hubble Space Telescope later observed Neptune in the 1990s, the Great Dark Spot had disappeared. It had simply vanished. In its place, new storms appeared elsewhere on the planet, Noka. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's storms appear transient. They form, they migrate, they dissipate. This instability suggests a complex and possibly chaotic atmospheric system. Neptune's atmosphere is composed primarily of hydrogen and helium, with small amounts of methane. Methane absorbs red light from the sun and reflects blue wavelengths, giving Neptune its characteristic color. But the exact depth and layering of Neptune's atmosphere remain uncertain. Above the visible cloud tops, thin haze layers exist. Beneath them, thicker methane clouds form at certain pressure levels. Deeper still, ammonia and water clouds may exist. However, these lower layers have never been directly observed. All models of Neptune's deeper atmosphere are based on indirect measurements and theoretical calculations. No probe has descended into Neptune's atmosphere to measure temperature, pressure, and chemical composition in detail. This lack of direct measurement leaves room for uncertainty. Pressure increases rapidly with depth. At a depth of only a few hundred kilometers below the cloud tops, pressure would exceed millions of times Earth's atmospheric pressure. Temperatures would rise accordingly. In these extreme conditions, water does not behave as it does on Earth. It does not form ice in the conventional sense. Instead, it may enter a supercritical phase, neither liquid nor gas, forming a dense, electrically conductive fluid. This exotic interior may help explain Neptune's unusual magnetic field. Neptune's magnetic axis is tilted approximately 47 degrees relative to its rotational axis. Furthermore, the magnetic field is not centered at the planet's core. It is offset. This creates a lopsided magnetic environment that changes orientation as Neptune rotates every 16 hours. By comparison, Earth's magnetic field is relatively stable and aligned closely with its rotational axis. The origin of Neptune's magnetic field is believed to arise from motion within a conductive fluid layer, possibly a superheated water ammonia ocean inside the planet. If this is correct, Neptune's internal structure is layered roughly as follows: a rocky core at the center. Above that, a mantle composed of water, ammonia, and methane under extreme pressure. Above the mantle, a thick envelope of hydrogen and helium. And finally, the upper atmosphere visible to telescopes. However, these layers are not solid boundaries. They blend under pressure. Transitions are gradual rather than distinct. Neptune's density suggests it contains a significant fraction of heavier elements compared to Jupiter and Saturn. This may explain why it is more compact relative to its size. The planet's rapid rotation contributes to slight flattening at the poles, though not as dramatically as Saturn. Neptune's gravity at the cloud tops is approximately 1.14 times that of Earth. That means a person standing hypothetically on a solid surface at Neptune's cloud level, if such a surface existed, would feel slightly heavier than on Earth. However, Neptune has no solid surface in the traditional sense. Like Jupiter and Saturn, it transitions from gas to fluid under pressure, without a defined boundary. Neptune's position at the edge of the solar system also places it near the Kuiper Belt. The Kuiper Belt is a region filled with icy bodies, dwarf planets, and remnants from the early solar system. Pluto resides within this region. Neptune's gravitational influence extends into the Kuiper Belt. It shapes the orbits of many objects there. Pluto, for example, is locked in a 3-to-2 orbital resonance with Neptune. For every 3 orbits Neptune completes, Pluto completes 2. This resonance prevents their orbits from crossing dangerously. Neptune acts as a gravitational gatekeeper. Its mass and position sculpt the outer solar system. If Neptune had formed slightly differently, if it had migrated inward or outward in early solar system history, the architecture of the Kuiper Belt would look different today. In fact, many planetary formation models suggest that Neptune may have migrated outward after forming closer to the Sun. This migration could have destabilized early Kuiper Belt objects, scattering them into new orbits. Some may have been sent inward, contributing to impact events in the early solar system. If that is true, Neptune may have played a role in shaping the environment of the inner planets long ago. Even from its distant orbit, Neptune exerts influence. Yet, despite its mass and power, Neptune remains observationally distant. Modern telescopes such as Hubble and the James Webb Space Telescope can capture improved images of Neptune. They can detect atmospheric changes and track storm formation. But these are distant observations. We do not have continuous in situ measurements. We do not have orbiters circling Neptune, mapping its magnetic field in detail, sampling its atmosphere, or analyzing its internal heat flux directly. And everything we know about Neptune comes from one flyby in 1989. Decades of remote telescopic observations, theoretical models based on physics and chemistry. That leaves enormous room for discovery. Consider this. Jupiter has been visited by multiple spacecraft, Galileo, Juno, and several flybys. Saturn was studied extensively by the Cassini mission for 13 years. Mars has hosted orbiters and rovers for decades. Neptune has had one visitor for a few hours. This imbalance in exploration means Neptune remains one of the least understood major planets in the solar system. Its internal heat imbalance remains partially unexplained. Its storm dynamics are not fully understood. Its magnetic field structure remains unusual. Its deep interior composition remains theoretical, and its position at the boundary of the Kuiper Belt suggests it may have shaped the outer solar system in ways we have yet to reconstruct fully. When we say Neptune may be hiding something, it is not necessarily something dramatic or catastrophic. It may simply be hiding complexity, hiding answers to questions we have not yet fully formed, hiding details that require proximity to uncover. At the edge of sunlight, Neptune continues its orbit. Every 165 years, it completes one slow circuit around the Sun. Every 16 hours, it rotates once, spinning its storms across dim skies. It radiates heat from within, though we are not entirely certain why. It shapes the orbits of distant, icy bodies. It maintains supersonic winds in darkness. And it does so quietly. No bright rings like Saturn's, No massive striped storms like Jupiter's. Just a deep blue sphere moving steadily in cold twilight. A world at the edge. And perhaps a world still keeping its secrets. Before we continue deeper into Neptune's hidden layers, if you're enjoying this slow journey through space, you can quietly tap subscribe. It helps this channel continue exploring the universe, one calm story at a time. Now, let's drift further into the darkness beyond the clouds. The fastest winds in the solar system. If distance from the sun determined atmospheric violence, Neptune should be calm, should be quiet, still, frozen. Instead, it is home to the most powerful winds ever measured on any planet in our solar system. Neptune's wind speeds can exceed 2,000 kilometers per hour. That is faster than the speed of sound on Earth. To understand how extraordinary this is, well, consider that the strongest hurricanes on Earth rarely exceed 250 kilometers per hour. Even Jupiter, a much larger planet receiving more internal heat, does not consistently produce winds that surpass Neptune's extremes. And yet, Neptune does. This creates another paradox. The sun is the primary energy source for atmospheric motion on Earth. Solar heating drives temperature differences. Temperature differences create pressure gradients. Pressure gradients produce wind. But at Neptune's distance, solar energy is minimal. The sunlight reaching Neptune is roughly 1/900th of the intensity of sunlight at Earth. So where does the energy come from? The answer begins beneath the clouds. Neptune emits approximately 2.6 times more energy than it receives from the sun. This means the planet is generating significant internal heat. That heat likely originates from residual energy left over from its formation, combined with slow gravitational contraction. As Neptune formed billions of years ago, gravitational collapse converted potential energy into heat. That heat has not fully dissipated. It continues to escape slowly into space. This internal heat rises through the planet's layers via convection. Convection occurs when warmer material rises and cooler material sinks. On Neptune, convection likely occurs within deep layers of hydrogen, helium, and volatile compounds such as water and ammonia. As heat escapes upward, it disrupts atmospheric stability. In combination with rapid rotation, this heat drives extreme wind systems. Neptune rotates once every 16 hours. And this relatively fast rotation enhances the Coriolis effect, the force that causes moving air to curve rather than travel in straight lines. On Earth, the Coriolis effect influences hurricanes and jet streams. On Neptune, with stronger winds and a different atmospheric structure, the effect is amplified. The result is a system of alternating wind bands that circle the planet. These bands are not as visually dramatic as Jupiter's colorful stripes. Neptune's atmosphere is more uniform in appearance due to its deep blue coloration and haze layers. But beneath that uniform color lies intense motion. Voyager 2 provided the first direct measurements of Neptune's wind speeds during its 1989 flyby. By tracking cloud movement across successive images, scientists were able to estimate wind velocities, when they observed winds reaching 1,500 to 2,100 kilometers per hour. Some winds blew westward, opposite the planet's rotation. Others moved eastward. This creates shear zones, boundaries where winds moving in different directions collide. Shear zones can generate vortices. One of the most striking examples of such a vortex was the Great Dark Spot. When Voyager 2 approached Neptune, it captured images of a massive dark storm system in the southern hemisphere. The Great Dark Spot was roughly the size of Earth. It resembled Jupiter's Great Red Spot in structure, though darker in color and likely shorter-lived. The Great Dark Spot was an anticyclonic storm, a region of high atmospheric pressure surrounded by circulating winds. But unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's Great Dark Spot vanished within a few years. When the Hubble Space Telescope observed Neptune in the 1990s, the storm was gone. In its place, new dark spots appeared in other latitudes. This suggests that Neptune's storms are dynamic and transient. They form, they intensify, they dissipate. Why are Neptune's storms so unstable compared to Jupiter's? One explanation involves differences in atmospheric depth and energy distribution. Jupiter's atmosphere is extremely deep, with stable band structures and powerful jet streams that can maintain storms for long durations. Neptune's atmosphere, while still deep, may have different vertical mixing properties. Another factor may involve internal heat flux. Because Neptune emits more internal heat relative to Uranus, its atmosphere may experience stronger convective bursts, where these bursts can create large storms, but may also destabilize them over time. Temperature differences across Neptune's atmosphere are surprisingly small, given its distance from the Sun. This suggests that internal heat dominates atmospheric energy more than solar heating does. On Earth, storms are largely driven by temperature contrasts between equator and poles. On Neptune, internal heat rising from below may create more uniform energy distribution, leading to global wind systems less dependent on solar latitude. Neptune's winds also challenge basic intuition. Despite the cold environment, molecular motion within the atmosphere remains sufficient to support extreme velocities. The atmosphere is composed primarily of hydrogen and helium, which are lightweight gases. Lightweight gases can accelerate more easily under pressure gradients. Additionally, low friction at high altitudes allows winds to reach higher speeds without being dampened by surface interaction. Because Neptune has no solid surface, there are no mountains, no land masses, no oceans in the conventional sense, nothing to slow the wind. Wind systems can circle the entire planet without interruption. The deep blue coloration of Neptune makes storm detection more subtle. Dark spots appear as slightly darker regions against the surrounding atmosphere. Bright methane clouds sometimes form near storm systems, rising higher and reflecting more sunlight. These bright clouds may act as tracers, allowing scientists to track wind motion. Neptune storms also migrate. Some storms have been observed drifting toward the equator before dissipating. Others remain confined to certain latitudes. The exact mechanisms governing storm formation and decay remain uncertain due to limited observational data. After Voyager 2, no spacecraft has revisited Neptune. All subsequent observations rely on telescopes from Earth or Earth orbit. The Hubble Space Telescope has captured periodic images showing new storm formations. Some dark spots appear in the northern hemisphere decades after Voyager's flyby. This suggests Neptune's atmospheric cycles may operate over long timescales. Given Neptune's orbital period of 165 Earth years, seasonal changes occur very slowly. Each season lasts about 40 Earth years. When Voyager 2 visited in 1989, Neptune's southern hemisphere was experiencing summer. Since then, the planet has progressed slowly into a new seasonal phase. Seasonal heating differences, though minimal compared to Earth, may still influence atmospheric dynamics. The combination of internal heat, rapid rotation, and long seasonal cycles creates a complex atmospheric system. Yet, we have only seen it in detail once. Consider how much we have learned about Jupiter's atmosphere through repeated missions. The Galileo spacecraft orbited Jupiter for years. The Juno spacecraft continues to provide high-resolution measurements of wind patterns and gravity fields. we have nothing comparable for Neptune. No orbiter mapping wind velocities over time. No atmospheric probe descending into its clouds. No long-term magnetic field measurements from close range. Everything we know about Neptune's winds is based on one flyby and distant telescope imaging. This leaves open questions. How stable are Neptune's jet streams over decades, when what drives the sudden appearance and disappearance of dark spots? How deep do the storms extend beneath the visible cloud tops? Are there deeper atmospheric layers with even more extreme dynamics? Neptune's winds are not just a curiosity. They are clues. Clues about internal heat transfer. Clues about fluid dynamics under extreme pressure. Clues about how ice giants function. Understanding Neptune's winds has implications beyond our solar system. Many exoplanets discovered around other stars are similar in size to Neptune. These mini-Neptunes, or sub-Neptunes, are among the most common types of planets observed. If Neptune's atmospheric behavior is unusual, it may reflect processes common throughout the galaxy. But until we study Neptune more closely, we are left with partial answers. A distant planet with supersonic winds, a world colder than almost anywhere else, yet more dynamic than expected. A sphere wrapped in storms that appear and vanish. A planet that defies assumptions about energy and motion. At the edge of sunlight, Neptune does not rest. It moves. It churns. It circulates heat from deep within. And in doing so, it challenges our understanding of how planets behave when removed from the sun's direct influence. The fastest winds in the solar system do not belong to the largest planet. They belong to the most distant giant, a world still turning in cold twilight and still hiding the full story of its power. A storm that appears, then vanishes. When Voyager 2 approached Neptune in 1989, it revealed something unexpected. A massive storm system, dark and oval-shaped, swirling across the southern hemisphere. It was called the Great Dark Spot, and at first glance, it resembled Jupiter's Great Red Spot, a giant anticyclonic storm large enough to swallow Earth. The Great Dark Spot was roughly 13,000 kilometers wide. Winds around it exceeded 2,000 kilometers per hour. It appeared powerful, stable, imposing. But unlike Jupiter's storm, which has persisted for centuries, Neptune's Great Dark Spot did not endure. Within a few years, it was gone. When the Hubble Space Telescope observed Neptune in 1994, the storm had vanished completely. No fading remnant, no shrinking spiral. It had simply disappeared. And in its place, new dark spots began forming elsewhere. This behavior remains one of Neptune's most intriguing atmospheric mysteries. Why do its storms appear and then vanish? To understand this, we must first examine what a dark spot actually is. On Jupiter, the Great Red Spot is a high-pressure system, an enormous vortex rotating counterclockwise in the southern hemisphere. It is sustained by powerful jet streams that confine it and feed energy into it. Neptune's Great Dark Spot was also a high-pressure system. But unlike Jupiter's atmosphere, Neptune's atmospheric structure may not provide the same long-term stability. Neptune's atmosphere consists of multiple layers. The uppermost layer is composed primarily of hydrogen and helium, with methane contributing to its blue coloration. Below this layer are deeper clouds composed of methane ice, ammonia, and possibly water vapor. Even deeper lies a thick mantle of superheated volatile materials. When internal heat rises through convection, it disturbs atmospheric layers. These disturbances can form vortices. A vortex is a rotating system of air created by pressure differences. On Earth, Hurricanes are vortices powered by warm ocean water and atmospheric instability. On Neptune, vortices are powered by internal heat and atmospheric shear, the interaction between wind bands moving at different speeds or directions. The Great Dark Spot was one such vortex. But unlike Jupiter, Neptune's jet streams may be less stable over long time scales. If the jet streams shift position, weaken, or strengthen, they can destabilize existing storms. Another factor may be vertical wind shear, differences in wind speed between atmospheric layers. Strong vertical shear can tear apart storm systems. On Earth, hurricanes weaken when vertical wind shear disrupts their structure. On Neptune, similar processes may operate. Because we lack direct atmospheric probes, much of this remains theoretical. We infer storm dynamics from cloud motion, infrared imaging, and computer models. What makes Neptune particularly unusual is that dark spots have reappeared in different hemispheres over time. In the early 2000s, Hubble detected new dark spots forming in the northern hemisphere. These spots also persisted for a limited time before fading. This suggests that Neptune's atmosphere undergoes cycles of storm generation. Some storms drift toward the equator before dissipating. Others remain at mid-latitudes. Seasonal effects may also influence storm formation. Neptune's axial tilt is about 28 degrees, similar to Earth's 23.5 degrees. This means Neptune experiences seasons. However, because its orbital period is 165 Earth years, each season lasts roughly 40 years. Voyager 2 visited during southern hemisphere summer. Since then, Neptune has slowly transitioned toward a new seasonal configuration. Seasonal heating differences, though weak due to the faint sunlight, may still influence atmospheric stability. Even small differences in temperature can alter convection patterns over long timescales. Another contributing factor may be Neptune's internal heat flux. Neptune radiates significantly more energy than Uranus. This internal heat drives convective currents upward through the atmosphere. Convective bursts may create storms rapidly. But if energy distribution changes over time, storms may lose support and collapse. The exact depth of these storms remains unknown. Do they extend hundreds of kilometers downward? Or are they confined to upper atmospheric layers? Without a probe descending into Neptune's atmosphere, we cannot directly measure their vertical structure. This uncertainty reinforces the idea that Neptune is hiding complexity. Storm formation on Neptune also produces bright companion clouds. Voyager 2 observed bright methane clouds near the Great Dark Spot. These clouds likely formed when rising air cooled and methane condensed into ice crystals. Such bright clouds can act as markers of updraft regions within larger storm systems. In some cases, bright clouds persist even after dark spots disappear. This suggests that atmospheric activity continues beneath the visible storm feature. Neptune's storms also move. The Great Dark Spot drifted westward at a speed of roughly 300 meters per second relative to surrounding winds. Our newer dark spots observed by Hubble have shown different drift rates. These variations indicate that Neptune's atmospheric circulation is not fixed. Jet streams may shift latitude over decades. Temperature gradients may change, wind speeds may vary. Unlike Jupiter, whose atmosphere has been studied repeatedly through orbiters, Neptune's storm cycles remain poorly constrained. We have snapshots separated by years. We do not have continuous data. This limited data makes it difficult to determine whether Neptune's storms follow predictable patterns or if they arise chaotically. It is possible that Neptune's atmosphere operates near instability thresholds. Small changes in internal heat flow could produce large atmospheric effects. This sensitivity could explain why storms form dramatically and disappear just as dramatically. But there is also the question of why Neptune's storms are dark. The dark coloration may arise from deeper atmospheric layers becoming visible through cloud thinning. Or it may involve unknown chemical processes producing darker compounds. Some scientists propose that photochemical reactions in the upper atmosphere may generate darker haze particles. However, the precise chemical mechanisms remain uncertain. Again, Neptune's distance limits detailed chemical analysis. From Earth, even powerful telescopes can only capture limited spectral information. Instruments can detect methane absorption bands and general atmospheric composition. But detecting trace compounds requires close-range spectroscopy. Neptune has not yet hosted such instruments beyond Voyager's brief encounter. And storm disappearance also raises questions about atmospheric energy dissipation. When a storm vanishes, where does its energy go? Does it disperse evenly across the atmosphere? Does it transfer to deeper layers? Or does it trigger the formation of new vortices elsewhere? The appearance of new dark spots after older ones fade suggests energy redistribution rather than complete dissipation. Neptune's atmosphere may operate as a dynamic energy network. Vortices could serve as temporary pressure relief structures. When one collapses, pressure imbalances may lead to the formation of another. These processes are common in fluid dynamics under rotation. But the extreme conditions on Neptune, low temperature, high pressure, hydrogen-helium composition, create unfamiliar regimes. Laboratory experiments on Earth cannot fully replicate Neptune's atmospheric environment. Computer models simulate atmospheric dynamics, but simulations depend on assumptions about heat flow and composition. If those assumptions are incomplete, models may miss important behavior. Neptune's vanishing storms are not merely visual curiosities. They represent gaps in our understanding. Each disappearing vortex is a reminder that we have only begun to map this distant world's meteorology. On Earth, weather forecasting relies on satellites, atmospheric probes, ground stations, and decades of continuous observation. On Neptune, we rely on occasional telescope images. And yet, despite limited data, Neptune continues to surprise. Dark spots emerge where none were seen before. Storms drift unpredictably. Bright methane clouds flare and fade, all under faint sunlight, all powered largely by internal heat. Neptune challenges the assumption that the energy input from a star determines atmospheric violence. It demonstrates that planetary interiors can dominate atmospheric behavior. At the edge of the solar system, storms appear and vanish without warning. A giant vortex can dominate a hemisphere for years and then dissolve into nothing. No debris, no remnants, just a blue atmosphere, smooth once more. Until the next disturbance forms. This pattern of sudden emergence and disappearance reinforces the theme. Neptune does not reveal itself fully. Its storms are transient. Its dynamics are elusive. Its atmospheric engine remains partly hidden. A storm that appears and then vanishes. Like a signal briefly breaking through static. Like a whisper from beneath layers we have not yet explored. And somewhere beneath those shifting clouds, deeper currents continue to move. Currents we have never seen. Currents that may hold the key to understanding what Neptune is truly hiding. The blue illusion. When we picture Neptune, we picture blue. Deep blue, almost luminous. A rich sapphire sphere suspended in darkness. Among all the planets in the solar system, Neptune appears the most vividly colored. Jupiter is striped in browns and creams. Saturn glows pale gold. Mars burns red. Uranus looks muted, almost washed in soft cyan. But Neptune stands out. It is darker, deeper, more saturated, and that color is not just beautiful. It is a clue. Neptune's blue appearance comes primarily from methane in its upper atmosphere. Methane gas absorbs red wavelengths of sunlight. When sunlight strikes Neptune, the red portion of the spectrum is absorbed. Blue light is scattered and reflected back into space. This selective absorption produces the planet's striking color. But methane alone does not explain everything. Uranus also contains methane in its atmosphere. Yet Uranus appears lighter, more pastel in tone. Neptune's blue is darker, more intense. This suggests there is something else influencing its coloration, possibly deeper atmospheric structure, possibly additional chemical compounds, possibly differences in haze layers. This is why some scientists describe Neptune's color as a blue illusion, because what we see is not a solid surface. It is light filtered through layers of gas, cloud, and haze. The color tells us about absorption and reflection, but it does not reveal what lies beneath. Neptune's atmosphere is structured in layers. The uppermost layer contains thin methane clouds and photochemical haze produced by ultraviolet radiation interacting with atmospheric gases. Below that, thicker methane cloud decks form where temperature and pressure allow methane to condense. Even deeper, ammonia and water clouds may exist. However, the exact depth and structure of these layers remain uncertain. Voyager 2's flyby provided valuable data, but it did not descend into the atmosphere. We have never sent a probe to measure Neptune's atmospheric chemistry directly beyond a few remote readings. The deep blue color hides this complexity. It smooths out detail. It conceals turbulence beneath apparent uniformity. If Neptune were closer to the Sun, and therefore brighter, perhaps we would have studied it more intensely, or perhaps missions would have been prioritized. But at its current distance, Neptune remains visually distant and observationally challenging. Even powerful telescopes struggle to resolve fine details. The James Webb Space Telescope has recently provided improved infrared images of Neptune. In infrared wavelengths, Neptune does not appear deep blue. Instead, its cloud structures and rings become more visible. The contrast shifts. This demonstrates that the blue we see is only part of the story. Color in astronomy depends on wavelength. In visible light, methane dominates Neptune's appearance. In infrared, heat and deeper atmospheric layers reveal additional features. This difference reminds us that Neptune's familiar blue face is only one layer of perception. There may be deeper phenomena concealed by optical limitations. Another factor influencing Neptune's color may involve photochemical processes. Ultraviolet radiation from the sun can break apart methane molecules in the upper atmosphere. This process produces complex hydrocarbons and haze particles. These particles can alter how light is scattered and absorbed. Some scientists suggest that additional unknown chromophores, chemical compounds that influence color, may exist in Neptune's atmosphere. These compounds may absorb light differently than methane alone. But without direct atmospheric sampling, this remains hypothetical. Neptune's color also changes subtly over time. Long-term telescope observations have revealed variations in brightness and hue. Between 2018 and 2022, Neptune's brightness decreased significantly in visible wavelengths. Then, unexpectedly, it began brightening again. The reasons for this dimming and brightening are not fully understood. Possible explanations include changes in cloud cover, haze distribution, or seasonal effects. Seasonal effects on Neptune operate slowly. Each season lasts roughly 4 decades. As Neptune moves along its orbit, different hemispheres receive slightly more solar illumination. Although sunlight is faint at Neptune's distance, small changes may influence atmospheric chemistry. methane condensation levels may shift. Cloud formation rates may vary. Haze layers may thicken or thin. These changes could alter the planet's overall brightness. But we do not yet have continuous, detailed monitoring to confirm precise mechanisms. This reinforces a pattern. Neptune's visible appearance provides clues, but those clues often raise new questions. The blue illusion extends deeper, and under increasing pressure, methane behaves differently. At great depths, methane molecules may break apart under extreme conditions. Laboratory experiments simulating Neptune's interior suggest that methane could dissociate into hydrogen and carbon. Under immense pressure, carbon atoms may crystallize into diamond. If this occurs, diamonds could form deep within Neptune's mantle. These diamonds, being denser than surrounding fluid, might sink toward the core. This hypothesis of diamond rain remains under investigation. But if true, it would mean Neptune's blue methane-rich atmosphere conceals exotic high-pressure processes beneath. The calm blue exterior hides an interior of extreme physics. The illusion of serenity masks violent compression. Neptune's atmospheric temperature at cloud tops is around -214 degrees Celsius, but temperatures increase with depth. Near the core, temperatures may reach 5,000 degrees Celsius. That is nearly as hot as the surface of the sun. This enormous temperature gradient creates strong convection. Heat rising from below interacts with methane-rich upper layers. Convection influences cloud formation. It may also influence color distribution. Regions of upwelling may appear brighter due to methane condensation. Regions of subsidence may appear darker. Thus, Neptune's blue is not uniform. It shifts. Storm systems alter reflectivity. Clouds appear as bright white streaks against the darker background. These clouds are likely composed of methane ice crystals. When sunlight strikes them, they reflect more light than surrounding gas. Bright clouds can form rapidly and dissipate just as quickly. Hubble has observed high-altitude methane clouds forming over dark spots. These bright clouds often precede or accompany storm systems. Their presence suggests strong vertical updrafts. But again, these are distant observations. We have not measured cloud particle size directly. We have not sampled methane concentration variations. The blue illusion also affects public perception. When people imagine Neptune, they imagine a smooth blue marble. But Neptune is not smooth. It is layered. It is turbulent. It is dynamic. The color simplifies the image. It hides detail. From a distance, Neptune looks calm. Up close, it is chaotic. This theme appears repeatedly. Distance creates illusion. Proximity reveals complexity. Neptune's color also influences energy absorption. Methane's ability to absorb red light means less heat from sunlight penetrates deeply. However, because internal heat dominates energy balance, solar heating is secondary. Thus, Neptune's blue coloration plays only a minor role in its energy budget. Yet it defines how we perceive the planet. It shapes how we imagine it. In visual astronomy, color is powerful. It becomes identity. Mars is red, Earth is blue, Jupiter is striped, Neptune is deep cobalt. But identity based on color can mislead. Neptune's blue face is a surface phenomenon. It tells us about methane absorption. It does not reveal internal convection patterns. It does not show magnetic field distortions. It does not explain why Neptune emits more heat than Uranus. It does not explain transient storms. It is a filter, a thin optical veil. Behind that veil lies physics we are still attempting to understand. Neptune's color also connects to its classification as an ice giant. Unlike Jupiter and Saturn, which are dominated by hydrogen and helium, Neptune contains a higher fraction of heavier elements: water, ammonia, methane. These compounds contribute to its density and internal structure. Methane at the top creates the blue appearance, but deeper layers may contain supercritical fluids, exotic states, neither liquid nor gas. Such fluids may conduct electricity. This conductivity may drive Neptune's unusual magnetic field. The tilted magnetic field suggests that internal dynamo processes operate in a layer not centered within the planet. This layer may be a conductive ocean of ionic water and ammonia. But again, we have not directly confirmed this. The blue illusion continues. We see a color. We infer composition. We hypothesize interior states. But the full picture remains incomplete. The James Webb Space Telescope has recently captured new infrared images showing Neptune's rings more clearly. In infrared, Neptune appears brighter in certain regions. High-altitude clouds stand out sharply. The contrast between visible and infrared imaging reveals that Neptune's appearance depends heavily on observational wavelength. This means the blue we associate with Neptune is only one interpretation among many. If human eyes were sensitive to infrared wavelengths, Neptune would look very different. Perhaps less serene, perhaps more structured, perhaps more complex. The blue illusion is a reminder of perspective. From Earth, Neptune appears as a smooth, distant sphere. But from within its atmosphere, one would experience violent winds, crushing pressure, rising heat, and possibly falling diamonds, all hidden beneath a calm blue face. The hidden ocean beneath the clouds. When we look at Neptune through a telescope, we see only its atmosphere. There is no solid ground visible, no continents, no oceans in the familiar sense, just clouds, methane haze, deep blue light. But Neptune is not just an atmosphere. Beneath its clouds lies something far more unusual. Not rock, not simple gas, but an ocean. Not an ocean of water as we know it, with waves and shores and tides under sunlight, but a vast internal ocean made of superheated, compressed fluid. To understand this, we need to step away from the idea of planets as solid worlds. Neptune belongs to a class known as ice giants. This term can be misleading. The ice does not mean frozen blocks like Earth's glaciers. It refers to volatile molecules, water, H2O, ammonia, NH3, methane, CH4, that were present as ices in the early solar system. When Neptune formed billions of years ago, it accumulated a large amount of these icy compounds. Under the planet's immense gravity, these materials did not remain solid. They were crushed, compressed, heated, transformed. Today, scientists believe Neptune has three primary layers. At the center, a dense rocky core, roughly Earth-sized in diameter. Above that, a massive mantle composed largely of water, ammonia, and methane under extreme pressure. And above that, an outer envelope of hydrogen and helium gas. The mantle is the key. That mantle may behave like an ocean, but not like Earth's oceans. Temperatures in Neptune's mantle may reach 2,000 to 5,000 degrees Celsius. Pressures may exceed millions of times Earth's atmospheric pressure. Under those conditions, water does not boil. It does not freeze. It enters a state known as supercritical fluid. A supercritical fluid is neither liquid nor gas. It has properties of both. It can flow like a liquid but diffuse like a gas. It can dissolve materials in ways neither phase alone can. Inside Neptune, water molecules are squeezed so tightly that they behave in exotic ways. In some models, the water layer may become electrically conductive. This is important because electrical conductivity inside a rotating planet can generate a magnetic field. Neptune's magnetic field is strange. It is tilted by about 47 degrees relative to the planet's rotation axis. It is offset from the center. It is asymmetrical. This suggests that the dynamo generating the magnetic field is not located in a simple central core, as it is on Earth. Instead, it may originate in this deep, conductive ocean layer. If true, that means Neptune's hidden ocean is not only massive, it is active. It moves. It circulates. Convection within this supercritical ocean may drive magnetic disturbances. This deep layer may also explain why Neptune emits more internal heat than Uranus. Both planets are similar in size and composition, yet Neptune radiates significantly more heat. Perhaps Neptune's internal ocean allows heat to escape more efficiently. Perhaps its core retained more formation energy. Or perhaps past collisions in early solar system history altered its internal structure. We do not know. This ocean, if we can call it that, remains theoretical. No spacecraft has descended deep enough to measure its properties. No probe has penetrated beyond the upper atmosphere. Everything we know comes from gravity measurements during Voyager 2's flyby, magnetic field observations, laboratory experiments replicating high-pressure water behavior, and theoretical modeling. But those models suggest something extraordinary. At pressures above about 1 million atmospheres, water molecules may dissociate into ions. Hydrogen atoms separate from oxygen. The resulting mixture becomes a conductive fluid. In some experiments, scientists have even created a form of superionic ice. In this phase, oxygen atoms form a rigid lattice, while hydrogen ions move freely through it, almost like a metal conducting electricity. If such a phase exists inside Neptune, it would represent one of the strangest forms of matter in the solar system. A hot, electrically conductive ocean, moving slowly under crushing gravity, hidden beneath a blue atmosphere. The depth of this mantle layer may extend thousands of kilometers. It represents the bulk of Neptune's mass. Above it, hydrogen and helium gases form a thick envelope. But below it lies the rocky core. The core may be about 1.2 Earth masses in size. It may consist of silicates and metals. Temperatures near the core may exceed 5,000 degrees Celsius. The boundary between core and mantle is not sharp. It transitions gradually under pressure. Neptune has no defined surface. If you attempted to descend into Neptune, you would first encounter thin upper atmosphere, then thicker methane clouds, then deeper layers of hydrogen and helium. Pressure would increase steadily. Temperature would rise. Eventually, gas would transition into fluid. The distinction between atmosphere and ocean would blur. There would be no shoreline, no point where you could stand, just increasing density, increasing heat, and eventually crushing forces beyond survival. Yet beneath that invisible threshold lies a dynamic interior, an ocean unlike anything on Earth. One of the most fascinating hypotheses about Neptune's interior is the possibility of diamond rain. Methane molecules contain carbon. Under extreme pressure, methane may break apart. Hydrogen atoms separate. Carbon atoms may crystallize. Laboratory experiments at facilities like the National Ignition Facility have simulated high-pressure conditions similar to those inside Neptune. And these experiments suggest that carbon can indeed form diamond structures under such conditions. If diamond crystals form inside Neptune, they would be denser than surrounding fluid. They would sink toward the core. Over time, layers of diamond could accumulate. Imagine billions of tons of diamond slowly falling through a superheated ocean. Invisible from space, unreachable, but real. If this process occurs, it would influence internal heat transfer. The movement of dense carbon crystals downward could release additional gravitational energy. That energy could contribute to Neptune's heat output. Again, this remains theoretical, but it illustrates how much may be hidden beneath Neptune's clouds. The planet's blue exterior hides physics that challenges laboratory understanding. It hides extreme states of matter. It hides conductive oceans. It hides possible diamond formation. And yet, we have only glimpsed it briefly. Voyager 2 provided gravitational measurements that helped estimate Neptune's internal mass distribution. From those measurements, scientists inferred density profiles. But the flyby lasted only hours. A dedicated orbiter could refine these measurements significantly. It could map gravitational variations over time. It could detect subtle changes in magnetic field strength. It could deploy atmospheric probes. None of that has happened. Neptune remains unexplored at depth. The hidden ocean remains unvisited. There is also the question of mixing. How stable is the boundary between Neptune's mantle and atmosphere? Does mixing occur between layers? Are there giant plumes rising from deep interior into the upper atmosphere? On Jupiter, deep storms appear to extend thousands of kilometers downward. On Neptune, we do not yet know how deep its vortices penetrate. If Neptune's internal ocean is dynamic, it may feed energy upward into the atmosphere. This could explain why Neptune's winds are so powerful. Internal heat rising through a conductive ocean could create buoyant plumes. Those plumes could reach upper layers, driving storm formation. Without a probe, we cannot measure vertical temperature gradients precisely. Everything remains inference. Neptune's internal ocean may also influence its magnetic field variations. Because the magnetic field is tilted and offset, it creates complex magnetospheric interactions with solar wind. Charged particles from the Sun interact with Neptune's magnetic field. This interaction produces auroras. Recent observations from the James Webb Space Telescope have detected auroral activity on Neptune. These auroras appear faint and localized compared to Earth's, but they confirm that Neptune's magnetic field is active. The hidden ocean may be responsible for that activity. Inside Neptune, under millions of atmospheres of pressure, physics behaves differently. Water molecules distort. Electrons shift. Hydrogen becomes metallic under compression. At extreme depths, matter may behave more like plasma than liquid. The distinction between fluid and solid may dissolve. And yet, from 4.5 billion kilometers away, Neptune looks simple, smooth, blue, calm. The hidden ocean challenges that simplicity. It reminds us that planets are not defined by their surfaces alone. Neptune's true identity may lie beneath its clouds, in its mantle, in its conductive ocean, in processes invisible to telescopes. The idea that Neptune may hide an ocean of superheated water is not poetic exaggeration. It is grounded in physics. It is consistent with density measurements. It is supported by high-pressure laboratory experiments. But it remains unconfirmed. And until we send a dedicated mission to Neptune, it will remain hidden. A world at the edge of sunlight, with an ocean that never sees the sky, an ocean under pressure so extreme that matter itself transforms, an ocean that may drive storms, magnetic distortions, and heat emission, an ocean that we have never seen. Perhaps this is what Neptune is hiding. Not something supernatural, not something alien in the sense of creatures, but something alien in physics. A form of ocean we have never touched, a state of matter we can barely recreate. And beneath that ocean, perhaps a core still glowing with energy from billions of years ago. Neptune turns slowly. Its hidden ocean circulates. Its blue clouds drift above it. And from Earth, we see only a colored disk. But beneath that illusion lies depth. And depth always holds secrets. Diamond rain in the darkness. Deep inside Neptune, far below the clouds of methane and the roaring winds, the pressure becomes almost impossible to imagine. Millions of times greater than the pressure at Earth's surface. Temperatures hotter than molten lava. Light cannot reach these depths. No spacecraft has ever descended there. And yet, through physics and laboratory experiments, scientists have begun to suspect something extraordinary. It may rain diamonds inside Neptune, not metaphorically, not as poetic exaggeration, but as a real physical process driven by extreme pressure and chemistry. To understand this possibility, we must begin with methane. Methane is one of the key gases in Neptune's atmosphere. It is responsible for absorbing red light and giving the planet its deep blue color. Methane is composed of one carbon atom bonded to 4 hydrogen atoms. At normal temperatures and pressures, methane is stable. But under immense pressure, chemical bonds behave differently. Inside Neptune, as one descends thousands of kilometers below the cloud tops, pressure rises rapidly. At depths where pressure reaches millions of atmospheres, methane molecules may begin to break apart. The hydrogen atoms separate from carbon, and when carbon atoms are compressed under extreme pressure, they can rearrange into crystalline structures. Diamond is one such structure. On Earth, diamonds form deep within the mantle under high pressure and temperature. Volcanic eruptions bring them to the surface. But the pressures inside Neptune are far greater than those inside Earth. Laboratory experiments have attempted to simulate Neptune-like conditions. In 2017, scientists used high-powered lasers to compress hydrocarbons similar to methane. The experiments generated shock waves that created pressure and temperature conditions similar to those believed to exist inside Neptune. The results showed the formation of tiny diamond particles. These results were repeated and refined in later experiments. The implication is clear. Under Neptune's internal conditions, methane may decompose into hydrogen and solid carbon. The carbon may crystallize into diamonds. If this process occurs naturally inside Neptune, the diamonds formed would be much denser than the surrounding fluid. They would sink, slowly, through the superheated ocean layer, falling toward the core like rain. But unlike rain on Earth, this would not be water droplets falling through air. It would be carbon crystals descending through a dense, supercritical fluid ocean under crushing gravity. Diamond rain. The phrase sounds dramatic, but the physics is plausible. And if it happens, it could influence Neptune's energy balance. As diamonds sink toward the core, gravitational potential energy is released. That energy converts to heat. This process is similar to how sedimentation releases energy inside stars and planets. If large amounts of carbon crystallize and sink, and the energy released could contribute to Neptune's excess heat emission. Remember, Neptune emits more than twice the energy it receives from the Sun. Scientists have long debated why Neptune emits so much more internal heat than Uranus. Perhaps diamond formation plays a role. Perhaps gravitational settling of heavy elements contributes to the heat difference. Uranus and Neptune are similar in size and composition, yet Uranus emits far less excess heat. Why? One hypothesis suggests that Uranus may have experienced a massive collision early in its history. Such a collision could have disrupted its internal layering, trapping heat inside. Neptune may have avoided such a disruptive event. Its internal convection may be more active. If convection in Neptune is stronger, it could promote methane breakdown and carbon separation more efficiently. Thus, Neptune's internal ocean may not be uniform. It may contain layers. Regions where methane-rich fluid circulates upward, regions where carbon crystallizes, regions where hydrogen separates. This is not confirmed, but it is consistent with experimental data and planetary modeling. Another fascinating possibility involves the size of these diamonds. In laboratory experiments, diamond particles formed at microscopic scales. Inside Neptune, however, given sufficient time and pressure, diamonds could grow larger. Some theoretical models suggest centimeter-sized diamonds may form. Others speculate even larger sizes may be possible over geological timescales. But because these diamonds would sink toward deeper layers, they would not accumulate near the cloud tops. They would vanish into the depths, forever hidden from observation. But the idea of diamond rain captures imagination. But the deeper significance lies in what it tells us about planetary interiors. Neptune is not simply a sphere of gas. It is a dynamic chemical reactor. Its interior is a place where matter rearranges under pressure, where familiar molecules transform into new states, where elements separate by density. This chemical differentiation may influence Neptune's structure over time. If carbon accumulates near the core, it could alter density distribution. Density distribution affects gravitational field strength. Gravitational field strength influences orbital dynamics of moons. It also affects magnetic field generation. Everything inside Neptune is connected. Pressure drives chemistry. Chemistry influences density. Density influences convection. Convection drives magnetic fields and atmospheric motion. And yet, we have never seen this directly. Everything we discuss remains hidden. Diamond rain would occur thousands of kilometers below the visible atmosphere. Even if we sent a probe into Neptune's atmosphere, it would likely be destroyed by pressure and temperature long before reaching the depths where carbon crystallization occurs. To truly confirm diamond rain, we would need indirect evidence. Improved gravitational mapping, detailed measurements of internal density gradients, precise modeling of heat flow. Future missions could provide some of these data. An orbiter around Neptune could map gravitational anomalies over time. A deep atmospheric probe could measure composition gradients. But reaching Neptune requires patience. It takes more than a decade to travel there. And missions to the outer solar system require significant resources. For now, diamond rain remains a plausible but unconfirmed phenomenon. But even if diamonds are not forming exactly as imagined, the broader idea remains valid. Inside Neptune, extreme pressures create unfamiliar chemistry, superionic phases of water, metallic hydrogen under compression, carbon crystallization, exotic states of matter that cannot exist naturally on Earth's surface. These processes are not unique to Neptune. Many exoplanets discovered around other stars are similar in size to Neptune. Sub-Neptunes and mini-Neptunes appear to be common in our galaxy. If diamond rain occurs inside Neptune, it may occur inside countless planets throughout the Milky Way. Understanding Neptune's interior could therefore inform exoplanet science, and it could reveal how common such exotic processes are. It could influence models of planetary formation. It could help explain observed mass-radius relationships of distant worlds. Neptune becomes not just a distant blue planet, but a laboratory for understanding planetary physics across the universe. The concept of diamond rain also reminds us of perspective. On Earth, diamonds are rare, precious, valued. Inside Neptune, if this process occurs, diamonds would not be rare. They would be a byproduct of pressure, abundant, unseen, unreachable. A world where what we consider precious is commonplace and meaningless. And yet, no human eye has ever witnessed it. No instrument has directly recorded it. It remains hidden beneath layers of gas and fluid, a process occurring in darkness. Neptune's hidden ocean may host this rain continuously. Bond carbon separating from hydrogen, crystallizing, falling, settling, adding heat, altering density, all while storms rage above, all while the planet rotates every 16 hours, all while the sun appears as a distant star in its sky. Neptune does not advertise these processes. It does not reveal them through bright colors or dramatic rings. Its blue face remains calm. Its winds remain powerful. Its storms appear and vanish. But beneath that surface lies chemistry under extremes, a world where matter behaves differently, where the familiar transforms into the extraordinary. Diamond rain is not simply a curiosity. It is evidence that Neptune is still evolving internally, that it is not a frozen relic, but an active, dynamic system. At the edge of the solar system, under faint sunlight, Neptune may be generating crystals in darkness, an invisible rainfall of carbon, falling toward a core we have never seen. This is what makes Neptune compelling. Not just its distance, not just its color, but the possibility that beneath its quiet exterior, processes unfold that challenge our understanding of matter itself. A planet hiding storms, hiding oceans, and perhaps hiding diamonds. The magnetic field that shouldn't exist. If Neptune's storms challenge our understanding of atmospheric physics, and its hidden ocean challenges our understanding of planetary interiors, then its magnetic field challenges something even more fundamental. Because Neptune's magnetic field does not behave the way a planet's magnetic field is supposed to behave. On Earth, the magnetic field is generated deep within the planet's core. Molten iron moves in slow, powerful currents. And because iron is electrically conductive, this motion creates a dynamo effect, generating a magnetic field that surrounds the planet. Earth's magnetic field is relatively simple in structure. It is tilted about 11 degrees from the planet's rotational axis. It is centered near the core. It produces the familiar north and south magnetic poles. Neptune does not follow that pattern. When Voyager 2 flew past Neptune in 1989, one of its most important instruments was a magnetometer. This instrument measured the direction and strength of Neptune's magnetic field. The data revealed something unexpected. Neptune's magnetic field is tilted by about 47 degrees relative to its rotation axis. That is not a small misalignment. It is dramatic. But even more surprising, the magnetic field is not centered within the planet. It is offset from the center by more than half a planetary radius. Imagine Earth's magnetic field not emerging from its core, but from somewhere closer to the surface, skewed, lopsided, unstable. That is what Neptune's magnetic field appears to be. This strange geometry suggests that Neptune's magnetic dynamo does not originate in a central metallic core like Earth's. Instead, scientists believe it is generated in a conductive layer much closer to the surface. That layer may be the superheated ocean of water, ammonia, and methane we discussed earlier. Under immense pressure, this ocean may become electrically conductive. If convection occurs within this conductive ocean, it could generate a magnetic field. But because this ocean is not centered symmetrically around the core, and because convection patterns may be uneven, the resulting magnetic field could be tilted and offset. This would explain the unusual structure observed by Voyager 2. However, this explanation remains incomplete. Because Neptune's magnetic field is not only tilted, it is also complex. Unlike Earth's relatively simple dipole field, resembling a bar magnet, Neptune's field contains significant higher-order components. This means its magnetic lines twist and warp more dramatically. The magnetic poles do not align neatly. The field strength varies significantly as the planet rotates. Because Neptune rotates once every 16 hours, its skewed magnetic field sweeps through space in a wobbling pattern. This creates a magnetosphere, the region of space dominated by Neptune's magnetic field that is constantly shifting. The magnetosphere interacts with solar wind. Solar wind is a stream of charged particles flowing outward from the sun. Even at Neptune's distance, solar wind still reaches the planet, though weakened. When solar wind encounters Neptune's magnetosphere, it is deflected. Charged particles become trapped. Magnetic reconnection events may occur. All of this creates dynamic electromagnetic activity around the planet. Auroras have been detected on Neptune. But unlike Earth's auroras, which appear near the poles, Neptune's auroras can appear at mid-latitudes due to the tilted field. Recent observations from the James Webb Space Telescope have confirmed faint auroral emissions. These auroras are subtle. They are not as visually dramatic as Earth's northern lights, but they are important. They confirm that Neptune's magnetic field remains active. They confirm that internal dynamo processes are ongoing. The existence of Neptune's magnetic field also provides clues about its internal layering. If the magnetic field were generated in a central core, we would expect a more symmetric dipole. The offset field suggests a dynamo operating in a shell rather than a sphere. This shell may be the ionic ocean layer. If that ocean is convecting unevenly, it could create asymmetrical magnetic output. This also raises questions about Uranus. Uranus has a similarly tilted and offset magnetic field. Both ice giants share this trait. Jupiter and Saturn do not. Earth does not. And this suggests that ice giants operate under a fundamentally different magnetic regime. Perhaps metallic hydrogen, abundant in Jupiter and Saturn, produces a different dynamo structure than superionic water in Neptune and Uranus. Perhaps the thickness and location of conductive layers matter. But we have only flyby data for Neptune. We do not have continuous magnetospheric measurements over time. We do not know how stable Neptune's magnetic field is over decades. On Earth, the magnetic field slowly drifts. Poles migrate. Field strength fluctuates. Magnetic reversals occur over hundreds of thousands of years. On Neptune, we do not yet know whether similar reversals occur. We do not know how fast its magnetic poles move. We do not know whether its dynamo fluctuates strongly over time. This uncertainty is significant because magnetic fields protect atmospheres. They shield planets from solar wind erosion. At Neptune's distance, solar wind is weaker. But magnetic interactions still shape atmospheric escape processes. Understanding Neptune's magnetic structure could help explain atmospheric retention over billions of years. The magnetic field also influences radiation belts. Charged particles trapped by magnetic fields can form radiation zones. Jupiter's radiation belts are intense. They pose hazards to spacecraft. Neptune's radiation environment is less studied. Voyager 2 detected radiation belts, but data were limited. Future missions could map Neptune's radiation zones in detail. This matters not just for science, but for engineering. Any spacecraft orbiting Neptune must survive its radiation environment. And the magnetic field also interacts with Neptune's moons. Triton, Neptune's largest moon, orbits within the planet's magnetosphere. As Triton moves through Neptune's magnetic field, electromagnetic interactions occur. These interactions may induce currents in Triton's interior. If Triton has a subsurface ocean, magnetic induction could provide evidence. Future magnetometer measurements during close Triton flybys could detect such signals. Thus, Neptune's magnetic field may help us understand not just Neptune itself, but its moons. And yet, despite all of this, we have only one detailed magnetic data set from 1989. One pass, one snapshot. Imagine trying to understand Earth's magnetic field from a single flyby, lasting a few hours. That is the scale of our knowledge about Neptune's magnetism. The tilted magnetic field reinforces a theme. Neptune does not conform neatly to expectations. Its storms are transient. Its winds are extreme. Its heat output is disproportionate. Its magnetic field is skewed and off-center. Each anomaly suggests internal complexity. Each deviation hints that Neptune's interior structure differs subtly from Uranus. Yet Uranus appears more subdued. It emits little excess heat. Its atmosphere looks calmer. What differentiates these two ice giants so dramatically? One hypothesis suggests that Uranus experienced a massive impact early in its history. Such an impact may have disrupted its internal convection, trapping heat. Neptune may have avoided that fate. Its convection may remain vigorous. That convection could sustain both internal heat flow and magnetic dynamo action. But without direct interior probes, we remain uncertain. Neptune's magnetic field is invisible to the eye. We do not see it when we look at the blue disk, but it shapes the planet's environment. It influences particle movement. It drives auroral phenomena. It hints at deep ocean currents thousands of kilometers below the clouds. It is evidence of hidden motion. Motion we cannot observe directly. Motion occurring under pressures that crush molecules. Motion generating electromagnetic energy that extends into space. This magnetic mystery strengthens the idea that Neptune is hiding something, not in a dramatic or ominous sense, but in a structural sense. Its internal engine operates differently. Its magnetic output reveals asymmetry. Its field geometry suggests layered convection zones. Its dynamo may not resemble any other major planets. The more we examine Neptune, the more we see patterns that deviate from expectation. And deviation is often where discovery begins. Neptune's magnetic field should not look like this, according to simplified planetary models. But it does, which means our models must adapt. And until we return to Neptune with orbiters and probes, much of this remains theoretical. The blue illusion hides the magnetic dance beneath. Invisible lines of force extending outward, tilting, wobbling, sweeping through space. A field that should not exist in this form, yet does. Neptune turns quietly at the edge of the solar system. Its magnetic poles drift across its surface. Its hidden ocean churns beneath the clouds. And far beyond its blue atmosphere, invisible magnetic lines stretch into darkness. Another layer of mystery. Another hint that beneath its calm appearance, a Neptune structure is more complex than we once believed. The moon that does not belong. Neptune may be hiding secrets within its atmosphere and beneath its clouds. But some of its most compelling mysteries orbit outside it. Far above the blue sphere, moving in silent defiance of expectation, there is a moon that should not be there. Its name is Triton. Triton is Neptune's largest moon. It was discovered only 17 days after Neptune itself, in October of 1846, by British astronomer William Lassell. At first, it seemed like a normal satellite, a moon bound by gravity to its planet. But as observations improved over time, it became clear that Triton is anything but ordinary. The first sign of something unusual lies in its orbit. Triton orbits Neptune in a retrograde direction. This means it moves opposite to Neptune's rotation. Almost every large moon in the solar system orbits in the same direction as its planet's rotation. This is because moons typically form from the same rotating disk of material that formed their parent planet. They inherit that direction of motion. Triton does not. It moves backward. and that simple fact changes everything. A retrograde orbit strongly suggests that Triton did not form alongside Neptune. Instead, it was captured. At some point in the distant past, Triton must have been an independent object, likely a dwarf planet, orbiting the Sun on its own path. Then, something happened. Neptune's gravity intercepted it. The capture of a large object is not a gentle event. It requires energy dissipation. For Neptune to capture Triton, Triton must have lost orbital energy, perhaps through interactions with other moons, or possibly through a three-body gravitational interaction with another object that was ejected. The capture would have been violent. Triton's arrival would have disrupted Neptune's existing moon system. Any original moons in stable prograde orbits may have been destabilized. Some may have collided. Some may have been ejected entirely. The current configuration of Neptune's moons may be the result of this ancient gravitational chaos. Triton itself likely experienced tidal heating during capture. As its orbit shrank and circularized, tidal forces between Neptune and Triton would have generated enormous internal friction. This heating could have melted interior ice. It may have created subsurface oceans. It may have reshaped Triton's surface. Today, Triton remains one of the most intriguing objects in the outer solar system. It is roughly 2,700 kilometers in diameter, slightly smaller than Earth's moon. But its composition is different. Triton is composed primarily of rock and ice. Its surface is covered in nitrogen ice, water ice, and frozen carbon dioxide. When Voyager 2 flew past Neptune in 1989, it also passed by Triton. The images it returned were astonishing. Instead of a heavily cratered, ancient surface, Triton appeared relatively smooth, geologically young, with strange terrain features. Even more surprising, Voyager 2 observed geysers, dark plumes rising several kilometers above Triton's surface. These plumes were likely driven by nitrogen gas escaping from beneath the surface. Sunlight weakly warms Triton's frozen crust. Beneath that crust, volatile nitrogen may sublimate into gas. Pressure builds. Eventually, gas escapes through cracks, carrying dark material upward. These nitrogen geysers create streaks across the icy landscape. This is cryovolcanism. Volcanism not driven by molten rock, but by volatile ices. Triton is one of the few known objects in the solar system with active cryovolcanic processes. Its surface temperature is extremely cold, around -235 degrees Celsius, colder than Pluto, colder than most other known planetary surfaces. And yet, beneath that frozen crust, activity persists. The existence of geysers suggests internal energy. Where does that energy come from? Possibly tidal heating. Even today, Triton's orbit may not be fully stable. It is slowly spiraling inward toward Neptune. Tidal interactions continue to dissipate energy. Over time, perhaps hundreds of millions of years, Triton will move closer and closer. Eventually, and it may cross Neptune's Roche limit, the distance at which tidal forces overcome a moon's structural integrity. If that happens, Triton could be torn apart. Its debris could form a massive ring system around Neptune, a future catastrophe unfolding slowly. But before that distant future, Triton may hide another possibility. A subsurface ocean. Several icy moons in the solar system are suspected to harbor oceans beneath their surfaces. Europa, orbiting Jupiter. Enceladus, orbiting Saturn. Perhaps even Pluto. Triton's relatively smooth surface and evidence of resurfacing suggest internal heat may still be present. If heat exists beneath its crust, it could maintain a liquid ocean layer beneath frozen nitrogen and water ice. Such an ocean would be hidden beneath tens or hundreds of kilometers of ice. And if such an ocean exists, it raises profound questions. Because where there is liquid water, even in darkness, chemistry becomes possible. Energy gradients exist, molecules interact. Life, at least microbial life, becomes theoretically possible. No one is claiming that Triton hosts life, but its geology and thermal history make it a candidate worth studying. Yet again, we have only one flyby's worth of data. Voyager 2 observed Triton for only a short period in 1989. Since then, no spacecraft has returned. Triton orbits Neptune at a distance of about 355,000 kilometers. Its orbit is nearly circular. But because it moves in a retrograde direction, tidal forces are slowly reducing its orbital distance. Unlike Earth's moon, which is drifting away from Earth, Triton is moving inward. This is unusual, and it reinforces the idea that Triton was captured rather than formed in place. Triton also has a thin atmosphere. It is composed primarily of nitrogen, with trace amounts of methane. This atmosphere is extremely tenuous. Surface pressure is only about 14 microbars, far thinner than Earth's atmosphere. Yet, even this thin atmosphere is dynamic. Seasonal changes occur. Nitrogen ice sublimits and recondenses. Atmospheric pressure may vary slightly over time. Because Neptune's seasons last about 40 Earth years, Triton experiences long-term seasonal effects as well. When Voyager 2 visited, Triton's southern hemisphere was illuminated. The northern hemisphere was in darkness. Since then, seasonal illumination has shifted slowly, but we have not monitored these changes continuously. Another striking feature of Triton is its cantaloupe terrain. Large regions of its surface are covered in dimpled, textured formations resembling the rind of a cantaloupe melon. The origin of this terrain remains uncertain. It may result from cryovolcanic processes, or from the slow freezing and contraction of subsurface layers, or from diapirism, buoyant ice rising through denser layers. Without detailed surface mapping, the explanation remains incomplete. Triton's density suggests it contains a significant fraction of rock mixed with ice. This rocky component may retain heat longer than pure ice. Radioactive decay within rocky material may contribute to internal warming. Combined with tidal heating, this could sustain subsurface liquid layers for extended periods. Triton is also thought to be similar in composition to Pluto. In fact, before Pluto was reclassified as a dwarf planet, Triton and Pluto were often compared. They share similar sizes, similar densities, and similar surface compositions. This strengthens the hypothesis that Triton originated in the Kuiper Belt, the same region where Pluto resides. If so, Neptune captured a former dwarf planet. That event may have reshaped its entire satellite system. Neptune's current smaller moons may have formed from debris created during Triton's capture. Triton, therefore, is not just a moon. It is an intruder, a captured world, a body that does not belong to Neptune's original family. And yet, it now dominates Neptune's moon system. Its gravitational influence shapes ring arcs. Its inward spiral will eventually alter Neptune's future. Its cryovolcanic activity hints at internal complexity. It may hide an ocean beneath its frozen surface. It may hold clues about Kuiper Belt formation. It may reveal how planets capture large bodies. And yet, we have barely studied it. One flyby, one moment in 1989, a handful of images, some magnetometer readings, then silence. Triton continues to orbit backward. Its surface continues to freeze and crack. Its geysers may still erupt. Its internal ocean, if it exists, remains hidden. Neptune may be hiding secrets within itself. But Triton may be hiding secrets in orbit. A moon that should not exist in its current form. A captured dwarf planet. A future ring system waiting to happen. A frozen world with possible warmth beneath. At the edge of the solar system, Neptune and Triton move together in quiet defiance of expectation. One, a blue giant with tilted magnetism and hidden oceans. The other, a backward-moving moon with geysers and darkness. Together, they form a system unlike any other. And we have barely begun to understand it. The moon that is slowly falling Triton does not simply orbit Neptune. It is slowly falling toward it. This is not dramatic in the human sense. It is not visible from afar. It is not happening quickly. But on cosmic timescales, it is inevitable. Triton's retrograde orbit, the fact that it moves opposite to Neptune's rotation, creates a long-term gravitational imbalance. When a moon orbits in the same direction as its planet's rotation, tidal forces often push it outward over time. This is what is happening to Earth's moon. It is drifting away at a rate of about 3.8 centimeters per year. But Triton moves backward. That changes everything. Because Neptune rotates faster than Triton orbits, tidal interactions between the two bodies remove energy from Triton's orbit. Instead of moving away, Triton is spiraling inward, very slowly, but steadily. Over millions of years, tidal friction inside Neptune and Triton dissipates orbital energy as heat. That lost energy causes Triton's orbital radius to shrink. Eventually, perhaps in 100 million to 1 billion years, Triton will cross what is known as Neptune's Roche limit. The Roche limit is the distance at which tidal forces from a planet overcome the structural integrity of an orbiting body. Inside this limit, gravitational forces pulling at the near side and far side of the moon become stronger than the moon's own gravity, holding it together. If Triton crosses that boundary, it will not simply collide with Neptune. It will be torn apart, pulled into fragments, shredded into debris, and those fragments could form a massive ring system around Neptune, far more dramatic than the faint rings it currently possesses. In other words, Neptune's quiet moon system may one day transform into something spectacular. But long before that distant future, Triton's inward migration has consequences. Tidal forces generate heat. As Triton moves closer, tidal stresses within its interior may increase. These stresses can deform the moon's crust. They can create fractures. They can sustain internal warming. This may help explain Triton's cryovolcanic activity. When Voyager 2 observed geysers erupting from Triton's surface, it revealed that the moon was not geologically dead. Despite its extreme cold, it was active. Nitrogen plumes rose several kilometers into space. Dark streaks were deposited on the surface. This activity suggests internal energy remains present. Part of that energy may originate from residual heat of formation. Part may come from radioactive decay in Triton's rocky interior. And part may come from tidal interactions with Neptune. As Triton's orbit gradually shrinks, tidal heating may vary. Periods of increased orbital eccentricity, slight deviations from circular shape, could enhance heating temporarily. This would create cycles of internal melting and freezing. Such cycles could help maintain a subsurface ocean. If Triton possesses a subsurface ocean, it would be buried beneath tens of kilometers of ice. The surface appears dominated by frozen nitrogen, water ice, and carbon monoxide ice. But below that crust, warmer layers may exist. If liquid water mixed with ammonia persists beneath the surface, it could remain stable for extended periods. The possibility of a subsurface ocean makes Triton one of the most intriguing objects in the outer solar system. Europa and Enceladus receive more attention because they orbit closer planets that have been explored extensively. But Triton shares many of their characteristics. It is icy, it shows signs of resurfacing, it exhibits cryovolcanic activity, it may harbor internal heat, and it orbits within a magnetosphere. Neptune's magnetic field interacts with Triton. As Triton moves through Neptune's magnetosphere, it experiences changing magnetic flux. If Triton contains a conductive subsurface ocean, magnetic induction may occur. That induction could generate measurable magnetic signatures. Such measurements could confirm the presence of liquid layers, but we have not returned to measure them. Everything we know about Triton's interior comes from gravitational estimates and theoretical modeling. Voyager 2's flyby was brief. It captured stunning images. It measured Triton's mass and size. It detected its thin nitrogen atmosphere. But it did not orbit. It did not linger. It did not probe deeply. Since 1989, Triton has remained largely unstudied. And yet, it may represent one of the best laboratories for understanding captured worlds. Its retrograde orbit is a reminder that planetary systems are not static. They are shaped by migration, collisions, and gravitational capture. Triton's arrival likely disrupted Neptune's original satellite system. Before Triton was captured, Neptune may have possessed a set of prograde moons similar to those of Uranus. When Triton entered Neptune's gravitational influence, its interactions may have destabilized those moons. Some may have collided with Neptune. Some may have been ejected into space. Some may have fragmented. The debris from those ancient collisions could have formed temporary ring systems. Over time, those rings may have reaccreted into smaller moons. Neptune's current irregular moons may be remnants of that chaotic era. Triton is therefore not just a moon slowly falling inward. It is evidence of past violence. Its presence implies a history of gravitational upheaval. It suggests that Neptune's system was once dramatically reshaped, and it hints that further change is inevitable. As Triton continues its inward spiral, tidal heating may intensify. Its orbit will shrink, its internal stress will increase, its surface may crack more frequently. Cryovolcanic activity could fluctuate. Eventually, when Triton crosses the Roche limit, the moon's fate will change permanently. Fragments will form rings. Those rings may glow in reflected sunlight. Neptune, currently ringed by faint arcs and thin bands, could one day display a bright, dense ring system, more dramatic than Saturn's, more luminous than anything it has now. But that transformation lies far in the future. For now, Triton remains intact, cold, icy, orbiting backward. It completes one orbit around Neptune every 5.9 Earth days. It rotates synchronously, always showing the same face to Neptune, much like Earth's moon does to Earth. But unlike Earth's moon, Triton's long-term future is inward, not outward. This inward migration may also influence Neptune's rotation over time. Angular momentum is transferred during tidal interactions. As Triton moves inward, Neptune's rotation may slow slightly. Over billions of years, such interactions subtly alter planetary dynamics. Triton's thin atmosphere is also unusual. It is primarily nitrogen, with trace methane. Surface pressure is extremely low, about 70,000 times thinner than Earth's atmosphere. Yet seasonal heating can cause nitrogen ice to sublimate. When nitrogen sublimates, it forms temporary atmospheric layers. When temperatures drop again, nitrogen recondenses. This creates seasonal cycles. Because Neptune's year lasts 165 Earth years, Triton's seasonal changes are slow. Decades may pass before a hemisphere transitions fully from winter to summer. Voyager 2 observed Triton during southern summer. Since then, seasonal shifts have progressed, but we have not continuously monitored the changes. There may be ongoing geyser activity, as surface deposits may be shifting, atmospheric pressure may be fluctuating slightly, but we do not know. Triton remains distant, and its inward spiral continues silently. Neptune may be hiding secrets within its interior, but Triton may be hiding secrets in its crust. If a subsurface ocean exists, it remains concealed beneath frozen nitrogen. If tidal heating fluctuates, it does so unseen. If magnetic induction signals ripple through its interior, we have not measured them. Triton is both a captured relic and a future catastrophe, a world that does not belong, a moon slowly falling toward destruction, and perhaps a world with hidden warmth beneath ice. At the edge of the solar system, Neptune and Triton form a fragile partnership, one turning with supersonic winds and hidden oceans, the other orbiting backward, slowly descending. Together they create a system unlike any other in the planetary family, and yet we have barely studied it. One flyby, one brief visit, then silence. Triton continues to move inward, imperceptibly, patiently, and Neptune continues to hold it in gravitational embrace. The rings that refuse to behave. When most people think of planetary rings, they think of Saturn. Bright, wide, layered, almost impossibly beautiful. Neptune's rings are nothing like that. They are faint, dark, fragmented, and in some places, incomplete. From a distance, Neptune appears alone, a deep blue sphere in darkness. Its rings are too thin and too dim to be seen easily from Earth. Even large telescopes struggle to confirm their existence before Voyager 2 arrived. In fact, Neptune's rings were suspected before they were directly imaged. During the 1980s, MONA astronomers observed distant stars as Neptune passed in front of them. These events are called stellar occultations. When a planet moves across the line of sight to a star, the star's light briefly dims. In some occultations involving Neptune, astronomers detected brief, unexpected dips in starlight before and after the planet itself passed by. This suggested something was there. Something thin, something not continuous, perhaps arcs of debris. But when telescopes searched for full rings, they saw little. It was only when Voyager 2 flew past Neptune in 1989 that the mystery resolved. Neptune does have rings, but they are narrow and dark, and some are not complete circles. Instead, they form arcs, segments of ring material clustered in specific regions, rather than distributed evenly around the planet. This should not be stable. Under normal gravitational dynamics, ring particles orbiting a planet spread out evenly over time. Collisions between particles and slight variations in velocity cause material to disperse. A ring arc, a dense cluster of material in one segment of orbit, should quickly smear into a full ring. And yet, Neptune's ring arcs persist. The most prominent arc lies within the Adam's ring. The Adam's ring is Neptune's outermost ring. Within it, there are several bright arcs, named Liberté, Égalité, Fraternité, and Courage. These arcs represent regions where ring particles are unusually concentrated. The existence of stable arcs suggests gravitational shepherding. Shepherd moons are small moons that orbit near rings and use their gravity to confine ring particles. Saturn has shepherd moons that maintain the sharp edges of its rings. Neptune also has shepherd moons. One such moon is Galatea. Galatea orbits just inside the Adam's ring. Its gravitational influence may create resonances that confine particles into arcs. Resonance occurs when orbital periods align in specific ratios. These resonances can create stable gravitational pockets. Within these pockets, particles cluster rather than disperse. but the stability of Neptune's arcs is still debated. Observations over time have shown that the arcs change. They brighten and fade. They shift position slightly. Some arcs appear to weaken over decades. This suggests that the system is dynamic, perhaps only temporarily stable. Unlike Saturn's rings, which are composed largely of bright water ice, Neptune's rings are dark. They contain a high fraction of radiation-processed material. This dark coloration makes them difficult to observe. Their darkness suggests they may be composed of organic-rich compounds. Cosmic radiation and micrometeorite impacts may alter ring particles over time. Neptune's rings are also relatively young, at least in geological terms. They may not have existed for billions of years. Instead, they may have formed from debris produced during the capture of Triton. When Triton entered Neptune's system, its gravitational interactions could have destabilized pre-existing moons. Collisions between moons could have generated debris. That debris may have formed temporary rings. Over time, some debris reaccreted into small moons. Some remained as rings. Neptune's current rings may therefore be remnants of ancient collisions. If Triton eventually crosses Neptune's Roche limit and breaks apart, a new ring system could form, far larger and more dramatic than the faint rings we see today. Thus, Neptune's rings may represent a transitional phase, a quiet moment between past chaos and future transformation. The structure of Neptune's rings also tells us something about its gravitational environment. Because the rings are thin and confined, Neptune's gravitational field must be relatively smooth. Large irregularities in gravitational distribution would disrupt the rings, yet the arcs remain. This suggests that despite Neptune's offset magnetic field, its gravitational field may be more symmetric, or at least stable enough to maintain ring structures. Neptune has 5 main rings: Gali, the innermost; Leverrier, Lassell, Arago, and Adams, the outermost. They are named after astronomers associated with Neptune's discovery. Unlike Saturn's wide, bright rings, Neptune's rings are narrow and diffuse. They contain dust-sized particles as well as larger fragments. Radiation pressure and solar wind likely influence the smallest particles. Without gravitational confinement, those particles would escape over time. Thus, Neptune's rings require ongoing replenishment. Micrometeoroid impacts on small moons may supply fresh debris. Collisions between ring particles may generate dust. The rings are not static structures, they are constantly evolving. Their darkness also absorbs sunlight rather than reflecting it. This contributes to their low visibility. From Earth, they are nearly invisible without advanced instruments. The faintness of Neptune's rings reinforces the planet's quiet image. No dramatic display, no bright halo, just subtle arcs, hidden against darkness. But subtle does not mean simple. The arcs challenge classical mechanics. They force scientists to refine models of orbital resonance. They demonstrate that even small moons can exert significant gravitational influence. They reveal that ring systems are not uniform across planets. Each giant planet has rings, but each ring system is different. Jupiter's rings are faint and dusty. Saturn's are bright and massive. Uranus's are narrow and dark. Neptune's are fragmented and arc-shaped. This diversity suggests that ring systems depend strongly on each planet's history. Neptune's history likely includes violent capture events, collisions, moon disruption, gradual inward migration of Triton. Its rings may be relics of those processes. They may also foreshadow future events. If Triton disintegrates in the distant future, Neptune's ring system could become far more substantial. Imagine a dense ring encircling Neptune, glowing faintly blue under distant sunlight. For now, Neptune's rings remain thin and quiet. But they exist. They remind us that even in emptiness, structure forms. Dust and ice particles, circling billions of kilometers from the sun, held in delicate balance by gravity, confined into arcs by tiny moons. Persisting against dispersion, Neptune's rings also interact with its magnetosphere. Charged particles trapped in Neptune's magnetic field may collide with ring particles. This interaction may alter particle surfaces. Over time, radiation may darken them further. But again, our data are limited. Voyager 2 provided snapshots. Since then, telescope observations have tracked some changes. But without an orbiter, we cannot monitor long-term evolution in detail. Neptune's rings are subtle. They are easily overlooked. But they are another piece of the puzzle, another indication that Neptune's system is dynamic, shaped by capture, shaped by tidal forces, shaped by resonance. The rings refuse to behave simply. They cluster when they should disperse. They persist when they should smear. They change when we expect stability. And like everything else about Neptune, they exist at the edge of sunlight. Faint, quiet, but not simple. The gatekeeper of the Kuiper belt beyond Neptune. The solar system does not simply end, it fades. The sunlight grows weaker. The planets stop, but debris remains. A vast region of icy bodies stretches outward beyond Neptune's orbit. This region is called the Kuiper belt. And Neptune stands at its inner boundary like a silent gatekeeper. The Kuiper belt begins just beyond Neptune's orbit, around 30 astronomical units from the Sun, and extends outward to about 50 astronomical units, perhaps even farther. It is populated by thousands of icy objects, dwarf planets, comets, fragments left over from the formation of the solar system 4.5 billion years ago. Pluto resides there. So do Eris, Haumea, Makemake, and countless smaller bodies. These objects are cold, dark, composed primarily of ice and rock. They move slowly around the Sun in elongated orbits. But many of them do not move randomly. Their paths are shaped, and the shaper is Neptune. Neptune's gravity reaches far beyond its visible atmosphere. It extends outward into the Kuiper belt. Objects in this region feel Neptune's influence even if they never come close to the planet itself. One of the most fascinating examples of this gravitational control is Pluto. Pluto's orbit crosses Neptune's orbital path. On paper, this sounds dangerous. Two bodies crossing the same path should risk collision. But Pluto and Neptune never collide. They are locked in a 3-to-2 orbital resonance. For every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This resonance ensures that when Pluto crosses Neptune's orbit, Neptune is always somewhere else. The gravitational rhythm keeps them separated. This is not coincidence, it is resonance. Resonance is a gravitational pattern. When two bodies have orbital periods in simple ratios, like 2-to-1 or 3-to-2, their gravitational interactions become predictable. Over time, these interactions can stabilize or destabilize orbits. In Pluto's case, resonance stabilizes. Neptune's gravity shepherds Pluto into a safe path. Pluto is not unique. Many Kuiper belt objects are in resonance with Neptune. Some are in 2-to-1 resonance, some in 5-to-2. These objects are called resonant trans-Neptunian objects. Their orbits cluster into patterns defined by Neptune's gravitational influence. This reveals something important. Neptune does not merely sit at the edge of the solar system. It actively organizes it. Its gravity sculpts the architecture of the Kuiper belt. Without Neptune, the outer solar system would look very different. Some scientists believe that Neptune did not always orbit where it does today. Planetary migration models suggest that early in the solar system's history, the giant planets shifted positions. Jupiter may have moved slightly inward. Saturn, Uranus, and Neptune may have moved outward. In this model, Neptune formed closer to the Sun than it is today. Then, through gravitational interactions with a massive disk of planetesimals, Neptune gradually migrated outward. As it moved outward, its gravity scattered Kuiper Belt objects. Some were pushed into resonant orbits, some were flung outward into distant regions, forming what is known as the scattered disk. Some may have been sent inward, contributing to the late heavy bombardment, a period of intense asteroid impacts in the inner solar system. If this migration occurred, Neptune played a major role in shaping planetary history. It may have influenced the impact history of Earth. It may have contributed to the delivery of water and organic molecules to inner planets. It's all from billions of kilometers away. This is the subtle power of gravity. Neptune's influence is not loud. It does not shine brightly. It does not dominate the sky. But it shapes trajectories. It alters paths. It defines boundaries. Beyond the Kuiper Belt lies an even more distant region, the scattered disk and possibly the Oort cloud. Some objects in these distant regions have unusual orbital clustering. This has led to speculation about another large planet, sometimes called Planet 9. Far beyond Neptune, the idea arises from observing unusual alignment in the orbits of certain distant objects. If such a planet exists, it would follow Neptune's legacy, discovered first through gravitational effects. But for now, Neptune remains the outermost confirmed giant. Its gravity creates structure in what might otherwise be chaos. The Kuiper Belt is not a random swarm. It has gaps, clusters, resonances, boundaries, all influenced by Neptune. Neptune's mass, about 17 times that of Earth, is sufficient to dominate nearby space. Its Hill sphere, the region where its gravity dominates over the Sun's, extends about 0.77 astronomical units. Within that sphere, moons can orbit stably. Beyond it, Neptune's gravitational influence still shapes trajectories over long timescales. The Kuiper Belt objects that cross Neptune's orbit are either destabilized or shepherded into resonance. Those that approach too closely may be ejected inward or outward. Neptune acts as a gravitational filter. Some comets that eventually enter the inner solar system originate in the Kuiper Belt. Neptune's perturbations may send them inward. These are known as short-period comets. Thus, Neptune indirectly influences what we see in our own skies. A comet streaking across Earth's atmosphere may owe its trajectory to Neptune's distant gravitational tug. The planet at the edge quietly rearranges the solar system. Neptune's migration may also explain the sharp outer edge of the Kuiper Belt. There appears to be a sudden drop in object density beyond about 50 astronomical units. Why does the Kuiper Belt seem truncated there? One explanation is that Neptune's outward migration swept material outward, clearing certain regions. Another is that formation processes simply did not extend farther. But Neptune's influence is central to these models. Understanding Neptune's past motion is crucial to understanding the solar system's formation. Yet again, we face limited data, and we have not measured Neptune's internal structure precisely enough to reconstruct its migration with high confidence. We infer from models, we compare to exoplanet systems, we simulate, but direct measurement remains sparse. Neptune's role as gatekeeper also reinforces the theme of hidden influence. It shapes objects we rarely see. It organizes distant debris. It stabilizes Pluto's orbit. It may have shaped Earth's bombardment history, all while remaining distant and faint in our sky. If you could stand on Pluto's surface and look outward, Neptune would appear as a bright, star-like object moving slowly against the background. Pluto would feel Neptune's gravitational pull constantly, locked in resonance, safe because of that rhythm. The outer solar system is not random, it is structured, and Neptune is one of its architects. The Kuiper Belt objects that survive in stable orbits do so in patterns defined by Neptune's mass and motion. Neptune is the last giant planet before interstellar space. It marks the boundary between the classical planets and the scattered icy remnants of formation. But it is not merely a boundary marker. It is active. It influences. It organizes. It shapes. This gravitational shaping may be Neptune's most subtle secret, because from Earth, Neptune looks isolated, a lone blue sphere at the edge. But in reality, it is deeply connected to the structure beyond it. It holds Pluto in safe resonance. It confines Kuiper Belt objects. It sends comets inward. It may have migrated outward and restructured the solar system long ago. Neptune is not quiet in its influence. It is quiet in its visibility. Its power operates through mathematics, through resonance, through orbital dynamics, through time. And perhaps this is what Neptune is hiding most effectively. Not just storms or oceans or diamonds, but its role as architect of the solar system's outer frontier. We will explore how little we have truly explored Neptune itself. Because despite its influence, only one spacecraft has ever visited. And that brief encounter left more questions than answers. At the edge of sunlight, Neptune continues its orbit, shaping worlds we rarely see, holding secrets not just within, but far beyond. And so we return to where we began, a distant blue world, turning slowly in darkness. Neptune does not glow like Venus. It does not command attention like Jupiter. It does not shimmer with bright rings like Saturn. It waits, 4.5 billion kilometers from the sun, wrapped in supersonic winds, hiding an ocean beneath its clouds, possibly raining diamonds in silence, guarding a moon that does not belong, shaping the frozen frontier beyond its orbit. We have visited it once. Only once. In 1989, a single spacecraft drifted past for a few hours. It gave us glimpses, storms, rings, Triton's geysers, a tilted magnetic field. Then it moved on, and Neptune returned to silence. There is something humbling about that. We live in an age of satellites and constant connection. We map mountains and oceans in detail. We send rovers across alien deserts. We study black holes in distant galaxies. And yet, one of the major planets in our own solar system remains largely unexplored. Neptune reminds us that distance still matters, that mystery still exists, that there are entire worlds we barely understand. Perhaps Neptune is not hiding something in the dramatic sense. Perhaps what it is hiding is simply depth. Layers of physics, layers of chemistry, layers of history written in gravity and time. A planet discovered by mathematics, powered by internal heat, surrounded by faint rings that refuse to behave, orbiting beside a captured moon slowly falling inward. It turns in the dark. It shapes the Kuiper Belt. It holds Pluto in resonance. It sends comets inward. It keeps its storms brief and its secrets long. And somewhere beneath its blue illusion, matter moves in ways we have never witnessed directly. Maybe that is what makes Neptune beautiful. Not what we know, but what we don't. The edge of sunlight is not the end of the story. It is the beginning of deeper questions. And perhaps one day, a new spacecraft will make the long journey outward. It will take years to arrive. It will send back signals delayed by hours. And slowly, patiently, it will reveal what Neptune has been keeping to itself. Until then, Neptune remains a quiet giant at the boundary of our understanding. A world of wind, an ocean, and magnetism. A planet still whispering through gravity. And now, as you rest, whether under city lights or beneath a clear night sky, remember that above you, beyond all the familiar stars, Neptune is there. Turning, waiting, holding its silence. If you enjoyed drifting through the outer solar system tonight, and you find comfort in these slow journeys through space, consider subscribing to the channel. It helps this quiet corner of science reach more curious minds. And if you'd like, tell me in the comments where you're listening from tonight. Well, it's always fascinating to think about how many different places on Earth are connected by the same sky, while Neptune turns far beyond it. Until our next journey into the deep. Rest well.